Cool, let me share my screen. Okay, can you guys see it?
Yep.
Okay, great. Yeah, thanks for joining the talk. I'm looking forward to telling you guys a bit more about big data and Hadoop, and getting your insights on it as well. Essentially, the talk will be about history and implementation of distributed data processing, which pretty much fits in with big data and Hadoop essentially. So the purpose of the talk will be to understand distributed data processing, specifically the challenges that comes with it, and then to see how Hadoop solves these challenges, and also to see what exactly Hadoop is. So talk will be split up into 3 different parts. The first is big data processing. So we're going to look at what is big data, where did it come from, what's the issues that it gives us, and then distributed storage and processing and how it solves those issues. Second one, we're going to have a look at Hadoop as an ecosystem and briefly introducing Hadoop, telling you guys what it is. And then lastly, we're going to have a look at 5 of the Hadoop technologies in quite a bit of depth. So yeah, that's pretty much it. Let's jump into the first part, which is data processing. So in order to understand big data processing, I think we first need to get a good idea of what exactly is big data. Now, big data is a term that's been going around for, quite a time, and I think actually lost a bit of its core essence in how it's being used. Everyone talks about having big data and using big data and stuff, but just to make clear we're on the same page, I'm quickly just going to define it, and that definition is going to consist of 3 parts. First of which is that big data is extremely large and diverse data sets. It is so voluminous that traditional data processing software cannot manage it. And then the third part, which is quite important, is which may be analyzed computationally to extract value in the form of insights or algorithms. And I think this is an important thing that people miss a lot, is the essence of big data and the purpose of using big data and going through all of the effort to process it comes down to the fact that we want to extract value from it, either from business insights or machine learning algorithms or whatever means. So summarizing this, big data is really big. Typically, we can't manage it with normal infrastructure or hardware we've got, and we should be able to get value from this data. So to give you guys an idea of what data growth is looking like at the moment, data growth in the world is exponential. So every year we're getting more and more and more data. And essentially we have to do something with it and process it to make it more, well, to get the values from it. So this infographic gives a good idea of the data that we're dealing with each day. This actually comes from I think 2020 or 2019. But at that stage, every day we had 500 million tweets being tweeted. And when you think about that data, it's not just the actual blob of text in the tweet. It's where did it come from? Where did they send it? Who sent it? Who viewed it? How long did they view it, etc. So, for every piece of data, there's a lot of metadata with it. Every day, there's 294 billion emails sent. We've got 65 billion WhatsApp sent. We've got 95 million photos and videos shared on Instagram. This is just pretty much our social media platforms. We've got stuff like Hydrogen Collector, Collider, gathering data. We've got smart cars, we've got smart watches, etc. So essentially the point is big data is valuable. There's a lot of big data out there, and the rate at which it's growing is just increasing. Now, based on this, there's 2 things. There's good news and there's bad news. Now, the good news is that big data and all of its goodness is here, so we can extract value, we can get insights, we can build machine learning algorithms, etc. But the bad news is that we actually now need to store this data and process it, which is becoming more and more complex as the size of the data grows. And that is essentially where the data engineer comes in. Now, I'm not going to go into too much details on what a data engineer is. The data engineer, I think in this context, what we need to understand is the guy who will be managing the data and essentially be working with the Hadoop ecosystem. So I'm quickly going to touch on this and also where does a data scientist fit in. And I mean, just in one slide, a data engineer is the guy who's responsible for the movement, the manipulation, and the management of data. So movement would be to get data from different source systems into a single data lake, moving data around between different departments in a company. Manipulation would be stuff like transferring this data into different formats. If a data scientist would need a subset of data, the data scientist or the data engineer would prepare this for him. And then the management of the data. So infrastructure, storage of it, authentication, protection, etc. Another quick point on data engineering and data science. So I think data scientists are kind of the superstars in the data field. They are the guys who write the nice model or extract the nice machine learning models and build AI and the robots that's going to take over the world. But I mean, not a lot of people realize that the data engineer is actually the kind of the backbone of data science to an extent. And the data scientist is very dependent on the data engineer. And the reason for that is the data engineer is the guy who, like we just saw, makes sure that we get all of this data, keeps it structured, prepares the data for the scientist, for the data scientist, and ensures that they can just basically plug in their algorithms into the subset of data that they actually need. So just, yeah, this is kind of just to give you a bit of context of where does the big data go to via the data engineer into the data scientist actually then uses it to extract the value. Okay, so like we said, we have big data, we can get a lot of value from it, but we have a few problems in terms of actually getting that value and storing and processing our data. And one of these problems, which is one of the big fundamental issues, which also led to the development of Hadoop, is essentially the storage of the data and then extracting that data and processing on a single machine these large chunks of data. So looking at the storage first, this graph gives us the size of hard drives over the last, about 60 or 70 years. And this has been growing exponentially. So if we look at 1980, our biggest drive that we had was about 450 megs. 20 years later, we were looking at about 17 gigs. And another 20 years later, we were looking at about 16 terabytes. So hard drives are getting bigger, you can say keeping up to the size of data we're dealing with. But the issue comes with reading this data. The read speeds on disks has not been keeping up with the growth of the disk sizes and the data sizes. So if we look at the 1980s, we had a read speed of 4.4 megabytes per second from your largest disk, which means you could read the full disk in a time of 5 minutes. 20 years later, we had a read speed of 100 megabytes per second, meaning we could read the largest disk in 11 hours. Going 10 years further, we are looking at a read speed of 200 megabytes per second, meaning we can read the largest disk in 22 hours. So essentially what this means is that if we want to store data of 16 terabytes, that's fine. If we want to analyze data of 16 terabytes, first of all, we're going to take 22 hours to read that data into memory to actually process it, problem one. And problem two is you're going to have a machine with 16 terabytes of memory to actually process that on a single machine. So I mean, that's pretty much the essence of this. It's data storage in a way that we can quickly read it, and also in a way that we can actually process it all at once. And that is essentially where our solution comes in, which is parallel data processing and parallel data storage. So we're going to go into a bit of details now on what does that actually look like and essentially how does it work. So on the left-hand side, let's say we've got a 1 terabyte disk with a file on that we want to store and analyze. In parallel data processing, essentially what we're going to do is we're going to split this up into 4 smaller pieces. Now, this is typically going to be much larger splits into much smaller pieces of data. But for this example, we're splitting it up into 4 pieces. Onto each of those pieces, we're going to add processing capacity. And what we're then going to do is we're going to enable the transfer of data between these pieces of data chunks, you can say. And essentially, we'll go into a bit more details on this just now. But essentially, what this enables us, going back to our 2 previous problems, is that if we've got this scenario here where we're breaking up our data into 4 smaller pieces of storage, we can essentially read our data 4 times faster than we would have been able to if it was 1 chunk of data. And secondly, our processing unit can actually keep this data, if it is small enough, in memory to process this data. And we would essentially process this data all in parallel. The only issue we've got now is that we will at some stage need to combine this data again during processing. And that's why we add data transfer capabilities between these. So this is kind of a very simplistic high-level overview of what we do with parallel data processing. Next, I'm going to go into a quick, more low-level kind of code example of how this actually is implemented. We're going to look at 3 examples moving from left to right. On the left-hand side, we're going to look at the typical single memory serial processing example of data. Next, we're going to go into shared memory parallel processing, which would be, for example, a multi-core machine. And then we're going to go lastly into distributed processing and how that actually works. So first example, single memory serial processing. The example we're going to look at is the following. So let's say we have a blob of data, which I'm representing as a list of strings. Each of these strings is a integer value as a string. Now, what we want to do is we want to sum up all of these string values in their numerical value. So what we'll have to do is get all of this data into memory. We would then convert these strings into integers by mapping over it. And then we would sum all of those integer values into a single value, which is the sum of all of them. Now, the 2 issues we've got here, if we can imagine that this list is an extremely large piece of data, so let's say it's an array of 50 gigs. The first problem is getting this piece of data into memory. So typically this would sit on a drive. We would have to put it into memory. So there's our first issue. The second issue is that mapping over this list of strings, if, for example, the to-end operation on our strings is a very computationally intensive operation, this would take a lot of time. Main reason being it's being processed serially. So that's kind of the 2 issues we want to solve first, is reading all of this data, which is going to take us a long time, being able to keep it in memory, and then also being able to process in a non-serial manner. And that is then when we go to our kind of first improvement step, which would typically be a parallel processed array on just a normal multi-core machine. So what we do here is we've still got our list of strings, which we'd have to read in. We get the length of this list of strings. And then we basically split this list up into 2 parts and then processing it on 2 cores. So on the first core, we would take the first part of the list, map over it and accumulate the values. On the second core, in parallel, we would take the last part of the list, map it, take it to ints, and then accumulate it. And then the last step would just be to to summarize, to sum this value, and there we've got it. So what this does solve is we are able to process these potentially intensive operations in parallel, but we still have the reading bottleneck of reading this blob of data into memory, and also keeping it into memory, which would be a shared memory on a single machine. And that's then where parallel or distributed processing rather comes in. What we would do in this case is we would have multiple nodes, so multiple machines. We would split our data into smaller chunks, like we can see with these two, and we would perform our computations only on the piece of data on each of the nodes. So this node would contain a subset of the data. We would process it, and we would sum it all. Same on this node, we would have it in parallel, and then we would pass these two results to, well, either one of these nodes or another node, and just combine the two of them. And essentially what this gives us is the ability to have a small piece of data. I mean, maybe we can have 100 nodes here, small piece of data, quickly read it in, keep it in memory, process it in parallel, and then just combine the results at the end. And that is essentially how we go to distributed parallel processing and how that actually solves our problems. So as a summary, shared memory, parallel processing, we split up the data, cores and threads would independently operate on it, and we combine it when it's done. Distributed processing, we would split the data over several nodes, and then the nodes would independently operate on those shards of data, and we would combine it. Cool, so quickly recapping, we have big data, we've got value in it, we've got challenges regarding it, we're solving it with distributed processing, and that distributed processing as an implementation is then where Hadoop kind of comes in. Hadoop is, like we'll see now, an ecosystem that gives us tools and technologies to actually enable us to perform distributed processing. Okay, so the origins of Hadoop came in the early 2000s. It was kind of inspired / based on a bunch of papers that was published by Google. I think most of you would possibly recognize these papers. But it was internal platforms that Google developed to help them with their issues regarding big data processing. And if we look at this quote at the top, which was released by them, it said that for Google, the primary driver for developing these systems was pure expediency. There simply were no technologies at the time capable of storing and processing the vast data sets it was dealing with. So that was Google's issue. They then developed these systems internally, published these papers, and that's when the open source community went and said, but well, cool, this is nice. Let's build on this and try and improve on it. And that's essentially where the founders or the creators of Hadoop went and said, but great, let's take this, open source it, and Hadoop kind of began. Now, the key innovations in these papers and systems by Google, which is kind of similar innovations required to solve the problems we mentioned earlier, and the solutions that parallel programming gave us, distributed programming rather, is the following. So the first is to distribute the data sets across many machines, making the data set splitting it up into much smaller pieces. Secondly, splitting up the computation that we want to perform on the data, so that each of these would be run on the data. Each of the computations would run on a machine, performing it on the data that is also stored on that machine. So that's kind of the three main things that these technologies from Google brought us. Cool, so that's kind of the foundation of Hadoop. Now we're going to look at what exactly is Hadoop actually, and how does the Hadoop ecosystem, what we're talking about, look like. So per definition, Apache Hadoop is a tightly integrated ecosystem, which we'll explain now, of different software products which is built to provide scalable and reliable distributed storage and distributed processing, which we've been speaking about. So quick note on the ecosystem and software products. This was kind of something that was a bit vague for me to understand initially. Hadoop is not a specific single technology. It's not a single platform. Hadoop is a ecosystem or umbrella of various software products that is built to address the problem and the implementation of distributed storage and distributed processing. And a good way you can look at it is almost like, for example, an Apple ecosystem. So Apple provides us with a bunch of products and services that is integrated with each other, and as a whole, solves a big problem as well as sub problems. So it's got products and services which address a specific problem. Maybe you can link them up. You don't have to use all of them. They work together, but essentially it's a ecosystem that kind of fits under a umbrella, give or take. Cool. So then going from this like framework and technologies into something a bit more concrete, let's look at what was Hadoop 1.0, which was developed in the early 2000s based on those papers. This was the actual Hadoop, which was originally created, and it consisted of three main parts. The first was data storage. So a distributed file system, enabling us to store a big chunk of data across multiple machines. The second one was distributed processing, so a way to take a single application or program or algorithm and perform it on these different pieces of data on different machines. And then the last part was to actually have a resource manager that could manage the allocation of resources on these different machines in a cluster, and allocate it to, let's say, specific applications that you wanted to run on these machines, which would execute on the pieces of data. Making this a bit more concrete, we can look at this architecture diagram of Hadoop 1.0. So the gray blocks would be different machines or different nodes. And on each of them would be one of these three different parts. So we would have the storage layer, which was implemented as HDFS. We would have the resource management layer, which was implemented as Hadoop Yarn. And then we would have the processing layer, which was implemented as Hadoop MapReduce. So essentially, coming back to the ecosystem, these are all different technologies, which all runs as different processes on the machines, but essentially works together to solve distributed storage and processing. Okay, so from there, the Hadoop ecosystem basically expanded and grew into Hadoop 2.0 or 2.0 plus, whatever you want to call it, which is essentially quite a large ecosystem of technologies that still address this primary issues of distributed processing and storage, but also started solving a bunch of sub problems and kind of related problems that came from either the technologies or the original issue. So we're quickly going to have a look at a few of these technologies just on a very high level. These are the ones we're going to look at. The Hadoop ecosystem is much bigger than this. And I mean, it's expanding as we speak. But these ones, I think, would be good if you just have a rough idea of what they actually are and when they fit in. The first ones we're going to look at is the core components. HDFS and Yarn, we just had a look at. HDFS is our distributed file storage, and it's in the storage layer. Yarn is our resource negotiator, that's on the resourcing layer. And then we've also got Zookeeper, which is a configuration service. And for those that don't know, Zookeeper is a distributed configuration manager. So essentially, if you've got something like a HDFS cluster, which consists of multiple machines, each running HDFS daemon, and they need to have synced up configuration, you would use something like Zookeeper to do that. Then we've got the computational framework layer, which we're going to have a look at MapReduce, which was the original computational framework. And then alongside that, Spark, which is a newer technology which was developed which is much richer, easier to use, optimizations that was included, etc. Cool. Then we've got the analytical SQL engines, which essentially was kind of a sub problem that they started solving. And that was the idea of running SQL-based queries on a distributed data set. I mean, previously, if we had a whole company's data in a single database, a data analyst or a business intelligence officer could come. He should only would have understood SQL, and he could run a query and say, give me the average sales per day across the previous few years. Now we've distributed our data across multiple nodes. We should possibly write a MapReduce program to actually give us this, which was difficult. People didn't understand it. Then they came and said, but let's do a SQL abstraction and kind of give a guy the opportunity to just write SQL queries that would abstract all of the data storage infrastructure and implementations below it. So that's where Hive and Impala comes in. The main difference between them is Hive takes your SQL queries and produces a MapReduce job from it, which goes to Yarn, which goes to HDFS. And Impala just has daemon processes running across your HDFS cluster and takes your SQL query and runs it directly on your cluster. Then we have the storage layer, which there's quite a few. We've got HBase, which is a NoSQL distributed database. Then we have Apache Solr, which is an enterprise search platform, again, on a distributed data set. We've got Apache Kudu, which is a column-orientated distributed data set. And then we've got Kafka, which I think most people would know, but it's essentially a distributed event store. Cool, so that is some technologies in the Hadoop ecosystem. What we're going to do now is we're going to have a look at 5 of the most important ones. And those are HDFS, Yarn, MapReduce, Spark, and Hive. And we're going to look at them from bottom to top, starting with HDFS. Now, HDFS, as we can see here, would be running on, like we've said previously, a cluster of multiple machines. What is HDFS? It stands for Hadoop Distributed File System, and it is a scalable, fault-tolerant, distributed file system abstraction for Hadoop. I'm quickly going to go into all of these. So scalable meaning it runs on a cluster. You can add nodes as you want to and scale it as your data needs increases. Fault tolerant. So if we have a blob of data, so let's say my text file.txt, if we add it to Hadoop, what it does is it splits this data blob into multiple smaller pieces, spreads it across our nodes, and then replicates this blobs across other nodes. So essentially, if one of our nodes fails, we've got a few backups and we can recover from that. Distributed, I think that's pretty much self-explanatory. And then file system abstraction. The reason for that is HDFS is essentially to the user, an abstraction of your normal file system that you've got. So under the hood, there's a lot of stuff going on and it's very complex. But for myself, I can use the command line as I would with my normal file system, upload files, copy files, etc. We'll get to that in a bit more detail just now. Few points on HDFS. So it's storage for big data on a cluster of, this is the important part, cheap, unreliable computers. It enables you to use normal commodity hardware to run HDFS on and store data for your big data needs. Secondly, just mentioned it briefly, but it blocks your data up. So it would take a file, break it up into smaller pieces of similar size across our machines. This is configurable, but it's typically 64, 128, or 256 megabytes in size. It implements the worm pattern, which stands for write once, read many. And essentially what this means is that HDFS is suited for adding a data blob and reading from it multiple times from multiple systems. It's not meant for updating a file or performing a vim via command line to change a line in the file. If you wanted to adapt the file or piece of data, you would typically write the MapReduce job, which pulls in your data, so reads it, changes it, and then writes it back once onto your file system. Looking at the architecture briefly of how HDFS would then actually be implemented. So starting from the bottom, we've got different data nodes, which would be different machines. They would all have the data blobs on. So that's this white blobs. They would be replicated. These data nodes could be spread up however they wanted to, creating a cluster essentially. On top of that, we've got the name node. The name node would be running on a separate node, and this is essentially you can say, your administrator or your kind of gatekeeper for HDFS. And what this does and how it works is, if you have a client which wants to write a piece of data to HDFS, it would first reach out to the name node, tell it that it's got myfile.txt of size 1 terabyte. Name node would then come back and say, cool, I've acknowledged this. Reach out to data nodes A, B, and C, which is located at these IP addresses, and write it to them. The client would then take that, reach out to these data nodes, and write directly to the data node. So nothing goes through the name node. It's more a administrator of the system. Reading would work exactly the same. So we've got a client. The client would reach out to the name node, get the locations for myfile.txt, then reach out to the data nodes and read the files, the file blobs from there, and then combine it. Now, what I mean when I say reach out to these nodes, all of these nodes has a HDFS daemon process running. These are all connected to the name node, configuration synced by Zookeeper, which we spoke about earlier. And this enables HDFS as a whole to speak to one another and facilitate this reads, writes, and syncing of metadata. Interaction of HDFS. So like I said earlier, it's essentially a file system abstraction for the user. You can do HDFS DFS, which would be your command if you had HDFS installed on a machine. And you can from there do a ls, make directories, copy, move, remove, copy from a local file system, etc. So essentially, if you wanted to add a piece of data and you didn't really know a lot about Hadoop low levels, you could essentially just use the CLI and, as you would with your normal file system, interact with it. Cool. Then next, we'll be looking at Yarn, which is the resource negotiator. What Yarn stands for is yet another resource negotiator. What it is, it's quite a bulky definition, but it's a large-scale distributed operating system designed for cluster management and resource scheduling. Now, I think we can distill this to essentially saying that Yarn is a distributed operating system. So like HDFS, it's a bunch of daemon processes with a main node, processes distributed across our cluster. And it is essentially responsible for understanding the state of resources across our cluster. So for each machine, how much RAM, CPU, etc. do we have per machine? How much do we have left based on processes running on that machine? And then if we wanted to have a application or algorithm run across this cluster, we would give it to Yarn, which would then on each node allocate resources for that specific application and then execute it. How this would look from a architecture perspective, if we've got two clients who each wants to run a distributed application, it would essentially reach out to Yarn for kind of administering or overseeing this. How Yarn would look is Yarn has a resource manager, which is like we had in HDFS, which was the name node, which is kind of the administrator or the gatekeeper. And then on each node, we would have a node manager. Now, if the client submits a application that it wants to run, the resource manager would go and spin up an application master on one of our nodes. It would work through the node manager to spin this up, and the application master would then kind of become the new manager for this application, which was submitted by the client. The application master would then go and speak to the resource manager, who would through the other node manager inquire about and then allocate resources in the form of a container on the other nodes, and the app master would then correspond with the containers to run the application in a distributed manner. And that could then be replicated over and over again as new applications are submitted. Cool, so moving upwards then, the next step would be to look at MapReduce. So just quickly recapping, we've got HDFS, which stores our data. We've got Yarn, which would allocate applications onto our HDFS nodes. And then we've got MapReduce, which essentially is the application which we would give to Yarn, which it would run on the data on HDFS. So MapReduce is essentially actually two things. First of all, it's a distributed programming model, and it is a computational framework to enable distributed computations across a cluster of machines. So what does this mean? First of all, MapReduce is a model, and that is a abstract model of how can we perform distributed computations. And it does that by saying we perform it in a sequence of mapping and reducing steps, which we'll come to in more detail just now. So that's kind of MapReduce as just a programming model. What Apache, or sorry, rather Hadoop MapReduce is it's an actual implementation as a Java library that you can use to implement the MapReduce model. You can implement that in order to get a Jar file, which you can submit to Yarn, which would then actually run this MapReduce model-based code in a distributed fashion. So looking at the model first, which is a functional programming model, most of you guys might be familiar with the MapReduce model, but I'm quickly going to run through it. So if we've got an input, which is a blob of data, in this case, a bunch of words, and we want an output as basically a set of these words and the amount of times they occurred in this blob of data. And we want to do this in a distributed fashion, we would use the MapReduce model. And what this would entail is, first of all, splitting up our data into smaller pieces. And this would kind of fit in with our HDFS we looked at a bit earlier. We'd split this up into smaller pieces. We would then come to the map part, where we would process each of these parts of data on their own. In this case, what we do is we just count the amount of times that each word occurs in this part of the data. We then shuffle it, which is typically a kind of a grouping of our data. In this case, we're just grouping all of the instances of dog, cock, cat, and rat by their own as they were counted across the split up pieces of data. And then the last step is to, just a second, I don't know, it's lagging a bit. The last step is to reduce our data then. In this case, just summing the amount of times each word was counted, and then lastly, combining the final result. So this is essentially the MapReduce model, also how it corresponds to distributed computing. And what the MapReduce framework is then is essentially a Java library that you can use to implement, as you can see here, mappers and reducers on a code level, which can then be combined into application that you can then run in a distributed fashion. So for us to actually go from this code implementation to running it on a cluster, we would compile this into a jar file. We would add our data onto the HDFS cluster, and we would submit our jar file to Hadoop and then to Yarn to actually run this, as we saw a bit earlier with how Yarn actually works. Cool, so that is MapReduce. Next we come to Spark, which is also a computational framework, just in, you can say, with quite a lot of improvement. So Spark is essentially a big improvement on MapReduce, but then also adds a bunch of additional functionality, makes it easier for the users. It's a bit more optimized in terms of resource usage, etc. So again, Spark is a distributed computational framework with an emphasis on specifically efficiency, resource efficiency, and usability from the programmer's perspective. A few points on Spark. So it was designed from the ground up for big data and data science implementations. The Spark API, which is essentially the library you'll use to implement the code, has many functional programming operations that you can use. So just like you have a map operation, a filter operation in your code, you would have this in the actual Spark API, which you can use, which Spark would then use from there to actually create the distributed application. Spark itself is implemented in Scala, but it has programming APIs in Scala, Java, R, and Python. And it focuses very strongly on in-memory data processing. Architecture, we're going to run through this very quickly. It's very similar to Yarn, essentially how Yarn is implemented. We've got a client which wants to run a Spark application, which let's say was written in Scala. That would work with the driver, which has the Spark context inside of it. Spark context is a code level instance, which provides you connections to the resource manager and the actual executors, which we'll get to now. We then have a cluster manager, which can be implemented as Yarn. We can also run it directly on Kubernetes, Apache, Mesos, or we can actually have Spark run as a standalone cluster manager. The driver would then interact with the cluster manager. And from there, we would have worker nodes, which would typically be located on the HDFS nodes. And then between these two, we would run our application on executors by breaking up our program or job into smaller tasks. How does the actual Spark application look like if it's written in Scala, for example? Very brief example. Let's say we've got a text file in HDFS. We simply specify it as SC, which is the Spark context. Read the text file. We can then do a flat map, which takes every line in the text file, splits it up by a space. We can then map over it, creating a tuple with a simple 1, and then reducing it by each specific word and just counting up. The counts, we can then go and just save it as a text file at a specific HDFS directory. So essentially this is really, really simple if you take into account what is actually happening under the hood in terms of HDFS having a text file distributed. We just simply read it in, map it, reduce it, and then just save it again. This is almost as if you're running this on your local machine. Now, the main advantages of Spark is that the data is kept in memory as far as possible, avoiding any intermediate I/O, and that's something that MapReduce actually does a lot. It's got a lot of reading and writing as it goes through its MapReduce stages. And then also the data flows that we write is represented as direct acyclical graphs. And this gives Spark the potential, and this is actually one of its big, you can say, benefits, is it gives us the potential to actually optimize this graph before it gets executed. So even if you don't understand the code that well, if you use the right Spark abstractions, it has the potential to optimize your program or your data flow in order to actually run it in quite an efficient way when it gets executed. A few things, Spark has additional libraries as well that you can use. So it's got the Spark core module, which we've briefly looked at now. We've got Spark SQL, which enables you to actually use HiveQL in your code to interact with your data. You can use Spark Streaming, which is used for processing of streams, MLlib, which is common machine learning algorithms, and then GraphX, which gives you graph operations and computations. Then lastly, we're quickly going to have a look at Hive. Hive is, like we saw earlier, the SQL layer abstraction for interacting with HDFS. Tool for executing SQL queries on distributed applications. I think it's pretty much straightforward. A few points on it is it makes it possible for SQL strong non-programmers, so typically business intelligence guys or, yeah, I don't know, data analysts in a company who wants to run SQL queries on distributed data stores. It allows analysts to, again, run queries in HDFS without writing and deploying code, which you would have to do with Spark or MapReduce. It's able to execute a subset of the SQL specification, and it supports common SQL concepts such as table joins, unions, subqueries, views, etc. Briefly, from an architecture perspective, how does it look? So these are the, you can say, interfacing ways we've got with Hive. So there's a CLI, there's a web interface, you can have a JDBC connection or interact via a Thrift server. All of these connections would then go into our driver, which is essentially the core of Hive. It has a parser, a planner, and an optimizer, which is typically things that you find in a normal SQL database. So SQL that you write will be parsed, the query execution will be planned, it will also optimize it, and then it'll move on to the actual execution of the query. And that's then where the Hive driver goes and creates either a MapReduce job from our parsed, planned, and optimized query, and then via MapReduce executed on your HDFS cluster on the actual distributed data sets. Interaction with Hive would look something like this. So very similar to SQL. We would create a table with certain columns, specify its row formats. We would then load the data from a local path. So you can have this file on a machine loaded into this specific records table. And then we can run a query and say for all of the records in the records table, all of the columns in the records table, where the temperature is not equal to that and has a specific quality, group it by year and give me the maximum temperature for that specific year. So essentially for a non-programmer who knows SQL, this is pretty much what you've got to run queries on a massive data set. And that's about it. So quickly recapping, we looked at big data processing. So what is big data? What's the issues with big data? And how does distributed storage and processing solve that? Secondly, we looked at the Hadoop ecosystem. So what is Hadoop and what's some of the components in it? And then we briefly ran through 5 technologies in the Hadoop ecosystem. Yeah, sorry, it was a bit of a speedy one. I actually wanted to cover all of this stuff, but we can move on to questions if there are any. Okay, I think that's it, Megan.